Hello and welcome to our lesson on parent functions and transformations. So what we're going to be looking at today is a general overview of lots of different specific functions that we encounter in mathematics so that when we see the equation of a function on paper, we have a pretty general idea of what that's going to look like in terms of its graph. Okay, so there are several specific functions that we encounter in mathematics, and just about all of them, not all of them, but most of them are going to be a transformation of some parent function. Okay, transformation, hopefully that's a word we understand, and clearly not a big enough blank for that giant word. Transformation. Okay, most of the functions that we encounter are just a transformation of some parent function. Okay, so we have these parent functions are like the basis for all of the functions that or most of the functions that we encounter. For example, y equals x. Y equals x is an example of a linear function, and it is the parent linear function. So it's the basis for all linear functions. All linear functions are going to be some transformation of this particular parent linear function. Okay. Now I know we have tools that graph for us, but just so we understand what happens with the linear function, we're going to graph this and the other parents using the old-fashioned make a table of values. Okay. So I'm going to just pick a couple negative, I'm going to pick 0 and then a couple positive to plug in, see what we get back, and then plot those points to create this picture. Okay. So our parent linear function, when I plug -2 in for x here, well, since x and y have to be equal, I'm going to get -2 back for y. Okay, same thing with -1, same thing with 0, same thing with 1, and same thing with 2. So when we go to plot these points, -2, -2, -1, -1, 0, 0, 1, 1, and 2, 2, what we see is a constant slope between those 2 points, right? For every 1 I rise, a 1 I run, every 1 up and 1 over, it's the same consistent change between the points every single time. And so that's what makes this function, or makes this graph linear. So we're going to connect these points. Now technically I only picked x values from -2 to 2 in the table, but we know that we could continue to pick smaller x's and larger x's. So we're going to connect these with a line that continues forever in both directions. Okay, so there's our parent linear function. Again, every other linear function that we graph is just some transformation of this one. So by adding something to this y equals x, like a y equals x plus 1, or subtracting from it y equals x minus 2, or multiplying x by a fraction, so like a 1/2 x, or whatever we do to it, it's still going to be a linear function, but it might be shifted up or shifted left, or maybe its slant increases or it decreases, or maybe it's got a negative slope so that it's a decreasing graph instead of an increasing. So their transformations are putting other numbers into the function could change it, but it will still be linear based off of this parent. Okay, so every linear function obviously is going to make a linear graph. Now, what is it that how are you going to know when you're looking at another function that it's linear? What we're looking at is x to the first power. Okay, so that's x to the first power that's creating that linear function. Now you can see in the next one we have x to the second power. So the x squared is a different type of function. It's going to make a different type of picture. So y equals x squared is our parent quadratic function. And maybe we remember, because I think we've seen a couple of these already, what the quadratic function looks like on its graph. But let's pick a couple negative, again 0 and a couple positive, and see what's happening here. So when I plug -2 in here, -2 squared is going to make a +4 for our output. -1 squared makes 1. 0 squared is 0, 1 squared is 1, 2 squared makes 4. So when I go to plot these points, at -2, +4, -1, 1, 0, 0, 1, 1, and 2, 4, we see a different shape being created here. Now again, I could keep picking smaller x's, so like -3 would go up to +9, and +3 would go up to +9, and this is just going to continue. So we can connect these, and these points are connecting to make a U-shaped graph that we call a parabola. So the U shape is called a parabola. And every time we graph a quadratic function, that's the y equals x squared in there, we're going to see a parabola. Now when we start putting other numbers in there, like y equals x squared plus 1, or y equals x minus 1 squared, or putting other things in there, it's going to transform that parabola so that it could shift, or it could be a wider parabola, it could be upside down, but every time it's a quadratic function, it's still going to make a parabola. Okay? So there's our parent quadratic, and again, we're looking for that y equals x squared to identify that quadratic. Alright, so this is another polynomial function. We had x to the first, we had x to the second, and now we have x to the third. So this is what we call a cubic function. X to the third power x cubed. Okay, what is a cubic function going to look like? So let's see. Let's pick our old reliables here, plug them in. Negative 2 being cubed is going to give us a negative 8. Negative 1 cubed is negative 1, 0 cubed is 0, 1 cubed is 1, and 2 cubed is positive 8. And if you wanted to use a calculator for that, you absolutely could. So negative 2, negative 8, we're going to plot our first point. Negative 1, 0, 0, 1, 1, and 2, 8. And again, this could continue, but it's going to continue to increase really fast. So we want to make sure we put arrows here because this keeps going. But that sort of, I don't know how to describe this shape, but it's, I don't know, sort of S-ish shaped graph is what a cubic function is going to look like. Okay, every time you graph a cubic function, it's going to sort of look like that, where we have, you know, opposite end behaviors. So we had the same thing happen with the x to the first, opposite end behaviors. The x to the squared, those end behaviors match. X to the third has opposite end behaviors, but instead of the linear, where it's the same every time, we have more of a curve in there because the cube changes the slope between the points. But again, if we start adding and subtracting from x cubed and multiplying it by things, we could transform that graph, but that's going to maintain that basic shape every time. All right, so we have an idea of what a cubic function looks like. Now, 2 to the x power is not technically a parent function. What we would technically be looking at is some number to the power of x, where that number could be a 2 to the x, or a 3 to the x, or a 4 to the x. They all will sort of behave the same way. The only number that we couldn't have for that base would be a 0 or a 1, but any other number as the base is going to behave like 2 to the x and any other what we call exponential function. Okay, so this is an example of an exponential function. Now, an exponential function has an exponent, unlike the last three, right? We have an exponent here, we have an exponent here, we've got an exponent here, but what's different about the exponential is the variable is the exponent. So this is an exponential, not just because it has an exponent, but because the variable is an exponent. Okay, so let's see what this exponential looks like. Again, technically the parent is some number b to the x power. We're just going to let b be 2 in this case because 2, 3, 4, 5, they all sort of behave in the same way, and you'll see what happens. So let's again pick our old reliables and see what's going on in this graph. So when I plug negative 2 in here, 2 to the negative second power. I don't know if you remember your exponent rules. Let me just use a calculator so you can see this. If you raise 2 to the negative second power, it gives you 0.25, or if you hit the little, well, it looks like a fraction in the blue here, you can convert that to a fraction. So it's a fraction of 1/4. Why is it a fraction of 1/4? If you remember your negative exponent rules, anytime we have a negative exponent, we're supposed to move that base to the other side of the fraction so we can make that exponent positive. So 2 to the negative 2 is really 1 over 2 to the positive 2, which is why we're looking at a 1/4. Okay? So the same thing happens with 2 to the negative first. 2 to the negative first means we have 1 over 2 to the positive first, which means we're looking at a 1/2. How about anything to the power of 0? Do you remember the rule? Again, you could use your calculator if you forgot, but anything to the power of 0, like 2 to the power of 0, is going to be 1. Anything raised to the power of 0 is 1. 2 to the first, that's not so bad. 2 to the first power is going to be 2, and then 2 squared is going to make 4. So at negative 2, our graph is at a fourth. At negative 1, we're up a little higher. Hard to see the difference there. 0, 1, we've got a point. 1, 2, and then 2, 4. Now, this is just a little piece of the graph we captured in the table, but again, we could keep picking smaller x's and larger x's. So what's going to happen as we pick larger x's? Well, 2 cubed is going to make 8, and 2 to the fourth would make 16, and as we go this direction, this number is just going to grow really fast. So maybe you're familiar with the term exponential growth. It starts to grow really fast because you're going to keep doubling and doubling that output. Now what's happening on the other side is a little different. So as the exponent gets smaller, right, so 2 to the negative 2 was 1 over 4. If we have 2 to the negative 3, we would have 1 over 2 cubed, which is 8. And 2 to the negative 4 would be 1 over 16, 2 to the fourth power. What happens as the exponent gets smaller is the bottom of the fraction is going to get bigger. So if the bottom of the fraction gets bigger but the top doesn't, that means we have a smaller and smaller and smaller fraction every time. Now, how small can the fraction get? Well, it's going to get infinitely small, but it can't ever get to 0 because there's always going to be a 1 in the top of the fraction. So what's happening on the other side of the graph here is we're going to be getting closer and closer to the x-axis, but it's not going to cross. Let me just extend that a little further. It's going to get closer and closer to the x-axis, but it'll never cross. So what we have is a barrier in this graph, and I think I mentioned this in the last lesson. That barrier we call an asymptote. And this one happens to be at the x-axis, which is where y is equal to 0. We can't have an output of 0 because no matter what we put in for x, it's going to get smaller and smaller, but can't get to 0. Okay? Every exponential function has an asymptote. Okay, it's going to have, in fact, a horizontal asymptote, just like this one does. Now, it could shift around based on transformations, based on adding and subtracting and multiplying numbers by that function. But every exponential function will have an asymptote and will sort of resemble what's happening in this picture. Okay, so when you see an exponential equation on paper, you should be thinking about the restrictions and then that shape of the graph. Okay. Next, this is our square root parent. This is our parent square root function. Do we know what the square root function looks like? I think we saw this one the other day too, in our domain lesson. So every other table so far I've picked negative 2 to positive 2. I could technically have picked whatever I wanted for x, but that's not going to be true here. Yeah, we did talk about this. What's the smallest number we can take the square root of? Well, the smallest number we can take the square root of is 0. So, and instead of having a graph that goes forever in both directions, this graph is going to have a starting point because there's a smallest number we can square root. So square root of 0 is 0. I can also square root 1 and get 1. Now I could put 2 in my table, but the square root of 2 is a decimal, and I don't want to have to graph that. So same with 3, which means I'm going to skip to 4, and the square root of 4 is going to be 2. And then I'm going to skip to 9. The square root of 9 is going to be 3, and that's probably good enough to make our picture. So we're going to have a starting point for this graph at 0, 0. And then we've got a point at 1, 1, and at 4, 2, and at 9, 3. And the graph will continue in this direction, okay, but not continue the other. So we have a starting point, an end point on this graph, and then it goes forever in just the one direction. And that's going to be true for every square root function. Okay, every square root function, because there's a limit on what we can square root, we'll always have this graph with an endpoint and then an arrow in just one direction. Now, again, it could move around based on what else we do to the function, but that captures the spirit, okay, of what the square root function is behaving like. Okay, cube root's a little different because it's unrestricted. So the cube root function, we can take cube roots of negatives. So cube root of, again, I showed you this the other day. If you go into functions and hit that nth root button, you can take the cube root of, let's say, a negative 8 and get a negative 2, or you can take the cube root of a positive 8 and get a positive 2. Okay, so we can put, I want to be strategic about what I put in my table, right? I can put in a negative 8. The cube root of negative 8 is a negative 2. I can put in a negative 1. Okay, cube root of negative 1 is negative 1. The cube root of 0 is going to be 0. The cube root of 1 is 1. And the cube root of 8 is 2. Okay, so negative 8, negative 2, negative 1, 0, 0, 1, 1, and 8, 2. Looks sort of like the cube function, but it's reflected over here around the x-axis and wrapping around the x-axis instead of the y-axis. But unlike the square root that has the starting point and goes in one direction, over here in the square root of positives are positive. Here, cube root of positives are positive, but we also have the cube roots of negatives that are negatives. So we have both sides of the picture. We're not just restricted to the one side. And every cube root function is going to sort of resemble that, where we have the infinite domain, and we sort of have the same hill shape that we see in the square root function, but it's extended to both sides because it's unrestricted. Okay? What else? We have a few more. Let's see. Yep, a couple more. So 1 over x, we saw this briefly. This is what we call our parent rational function. So rational function means we have x basically in the denominator of fraction. We have a rational means fraction, right? Rational numbers are numbers we can write as fractions. So rational functions typically have fractions of polynomials. So what we want is to see x in the bottom of a fraction to make it rational. And that's going to create a restriction just like our square root had a restriction. So I could put negative 2 in my table, and 1 over negative 2 is going to be a negative 1/2. I could put negative 1 into my table. 1 over negative 1 is going to be negative 1. But 0 in the table creates an issue, right? If I have 1 over 0, that's not defined. I can't have one part of nothing. 0 in the bottom of the fraction is undefined, which means we won't have a point in this graph at 0. Okay? And we'll come back to what that creates, but let's leave that for a second. I can put 1 in. 1 over 1 is 1. I can put 2 in. 1 over 2 is going to make a half. Okay? So if we plot what we have, let's see, negative 2 and negative 1/2. Negative 1, negative 1. 0, I can't do anything. 1, 1, and then 2, and then a half. I don't really know if that's enough for us to see what's happening. Okay, so if we were to continue, let's continue this side. If I put in 3, I get a third. Put in 4, I get a fourth. Put in 5, I get a fifth, right? So what's happening is, again, my fraction is going to get smaller and smaller. So we're going to get closer to the x-axis this way, but the larger I go, the smaller the fraction gets. Again, I cannot get to the x-axis there. And the same thing is going to happen this way. It's just going to be negative. So what we see happening is another barrier, another asymptote. And then what's happening in the other direction? In between, what's happening right in there, okay? In between 0 and 1. What's happening in between these two values? Well, let's see. If I was to put in, get rid of this. If I was to put in a half, if I had 1 over a half, 1 divided by the half is the same as 1 times 2, right? How many halves are in 1? That'd be 2. So when I go to a half, my graph jumps up to 2. 1 over a third is going to be 3. 1 over a fourth is going to be 4. And what's going to happen on this side is we're just going to get bigger and bigger and bigger and bigger and bigger. Okay, and this same thing, the smaller and smaller the fraction gets, the larger that value gets. But I can't get to 0. All right, we said 0 on the bottom of the fraction is going to be undefined. So I could pick a smaller and smaller fraction. That graph continues to grow, but I can't get to 0. So not only does this graph have a horizontal asymptote, it also has a vertical asymptote. So with our rationals, we can see multiple asymptotes, and that's exactly what's happening here. So this is a vertical asymptote at the y-axis, which is where x is equal to 0. And then we have a, not a vertical, this is going to be a horizontal asymptote at y equals 0. Okay, so every time we graph a rational function, this is sort of the basis for what's going on. Now again, it can be transformed, it can move around and reflect, and actually we can create more restrictions depending on what we put into the bottom of the fraction, but rational functions are going to create these graphs that have asymptotes, and then the actual pieces of the graphs, these we call branches. So there's two branches of the graph that are beside these asymptotes, okay? So those are the strain ranges. And again, we're going to get into more detail with these function types as we go through some of our other modules. So we just are trying to give a general concept, all right? Last one we should be familiar with is what we call an absolute value function. That should make sense for a name since this is the absolute value of x. Unrestricted, right? I can pick this time whatever I want for x, plug it in, and get a y value back out. So if I put negative 2 in, what's the absolute value of negative 2? Positive 2. Absolute value of negative 1? 1. Absolute value of 0 is 0. Absolute value of 1 is 1. Absolute value of 2 is 2. So something similar to our quadratic happens here, where we have sort of this mirror image concept. Okay, but let's put it on the paper. So negative 2, 2. Negative 1, 1, 0, 0, 1, 1, 2, 2. And if I put 3 in, I'd get 3, 4 would make 4, and this is going to keep going in both directions in the same fashion. So it's sort of like the quadratic where we have some symmetry happening, but it's linear on both sides. So instead of making a U shape, it makes a V shape. And every time you graph an absolute value function, that's what's going to happen. It's going to make a V-shaped graph. Okay? We don't have a name for the V-shaped graph, and again, it can move around depending on what else we put into that function, but you should sort of have a concept in your head. So when you see the absolute value function, that you know it's going to make a V-shaped graph. Okay? Now, I've been mentioning transformations. What particular transformations am I talking about? Well, when you take your function and you add to it, it's going to make your graph shift up. When you take your function, you subtract from it, it makes your graph shift down. And when you add or subtract within the function, and I'll show you these in a second, it makes your graph go left and right. This makes our graph go to the left. This one makes our graph go to the right. When you multiply by a negative, it makes your graph reflect over the x-axis. When you multiply inside of the function by a negative, it makes it reflect over the y-axis. Again, I'll show you these in a second. When you multiply your function by something bigger than 1, it creates what we call a vertical stretch of the graph. And when you multiply your function by a fraction between 0 and 1, so where the numerator is smaller than the denominator, then it creates what we call a vertical compression of the graph. Okay? So let me show you what I'm talking about here. So let's say we wanted to look at the parent function. Let's look at y equals the square root of x. Okay, y equals square root of x. We've seen this before. We have a concept of what's happening in that graph. If I was to take that same function, y equals the square root of x, and then just add to it. If I was to add 1 to it, what happens? Well, the new one in green is the exact same function, but all the outputs are shifted up 1. Should make sense. If I add 2, now they're shifted up 2. If I add 3, they're shifted up 3. So that's what's happening in this first bullet. Okay, what we're saying is whatever parent function we have, if we add to it, it makes that parent function shift up. And that's true for every function. So I could put the parabola in there and shift the parabola up. Or I could put the cube root function in there and shift it up 3. Okay? This is just an easy one to see all these transformations. So then the opposite would happen if I subtract from it, right? Subtract 2 makes it shift down 2. Subtract 4 makes it shift down 4. Subtract 6 makes it shift down 6. So that's what this bullet is saying. If you take your function, like the square root of x, and subtract from it, then you're going to shift that graph down. Okay. Now the other addition and subtraction, the next two bullets, is happening within the function. So instead of subtracting from the function, you're going to subtract from the x value. So if we put, let's say, a minus 2 inside of the square root, so subtract it from the x and not the function, then we saw the green one shift to the right 2. If I subtract 6, it goes to the right 6. If I subtract 8, it goes to the right 8. And if we were to add 2, it goes left 2. Add 4 goes left 4. Add 6 goes left 6. Okay, that's what those next two bullets are saying. If we add to x and subtract to x, add to x makes the graph go left, and subtract from x makes the graph go to the right. Okay? Next one's saying take your function and multiply it by a negative. So let me get rid of this. If I take my function and multiply it by a negative, what happens? Well, the graph is upside down. We say that is a reflection over the x-axis. It's making a mirror image over the x-axis. Okay, now the next one, that's what this one says. Multiply your function, the whole function f of x, whatever it is, by x. The next one's saying multiply x by a negative. So if I move the negative inside, then instead of reflecting over the x, it reflects over the y-axis. Okay, and again, these are going to be true for every function. If I multiply the function by x, it reflects over the x-axis. Or by negative, it reflects over the x-axis. If I reflect... let me start that over. If I multiply a function by a negative, then it will reflect over the x-axis. If I multiply x by a negative, then it's going to reflect over the y-axis. Okay, I was trying to talk too fast. Sorry. Okay, now the next two bullets are taking your function and multiplying it by a number. If we take the function and we multiply it by a number that's bigger than 1, so let's say we multiply it by 2. What happened to the one in the green is, well, now the graph is sort of increasing faster. It's a little higher there. Multiply by 3, goes up even more. By 4, up even more. We call that a vertical stretch. If you took your graph and you stretched it vertically, so vertically is this way, right? If I just took the blue one and pulled it vertically, that stretch of the graph, that's what's happening when you multiply by a number that's bigger than 1. And now instead of stretching it, by multiplying by something bigger than 1, if you multiply by a fraction that's between 0 and 1, like maybe you put a half here, if you put a half in front, then now it's compressed, right? The graph is now moving slower than it was before. So if we took the blue one and we squished it down, if we compressed it vertically, that's going to happen every time you multiply by a fraction that's between 0 and 1, so maybe like 3/4. Right? And the smaller we make the fraction, let's say 3/15, the smaller we make the fraction, the more compressed the graph is going to get. Okay? And again, true for every parent function. So let me just throw another one in here. If we started with our parabola, okay, and we took our parabola, x squared, and again, if we multiplied it by a number bigger than 1, it's going to stretch it. If we multiply it by some fraction between 0 and 1, it's going to compress it, squish it down, make it wider. Okay, true for all parent functions, these transformations. And it's really nice to know them so that, again, when you're looking at a function, you have a concept of exactly what's happening on the graph, but it's not necessary that you memorize them, because you technically could do what I'm doing here, look at the parent function, look at the changes, and see how they affect the graph. Okay? So let's just try to identify, this is really generic here, if we took some function, and then multiplied it by 3 and added 1, what would be the result? Well, the times 3 here is going to vertically stretch the graph by a factor of 3. It's going to be increasing 3 times as fast. And the plus 1 here is going to shift everything up 1. So this is a translation up 1. Okay, so again, let me just show you. This is some generic, any function, okay, but let me just show you with, again, let's say the square. So if I took x squared, there's my parent. If I took it and multiplied it by 3, what happens? It's skinnier than it was. Well, let me put them both in so you can see. Okay, if I took y equals x squared, oh my goodness, x squared, okay, so now we have a black one to compare. If I multiply by 3, that's what it says, what happens? The black one now is stretched compared to the purple one, which is the parent. And then if I also added 1, then it shifts everything up 1. Okay, so we don't technically have to memorize these, we can see what's happening. Pick anything you want for f of x and you're going to see these transformations. Okay. Next one, we've got 3 things happening. First, we've got a negative. That negative is outside of the function. It's not with x, it's outside. So that's going to reflect over the x-axis. And the 1/3 is going to create a vertical compression. So it's vertically compressed. And then that minus 4 now is subtracting 4 from the x. That makes the graph go to the right, translates to the right 4 units. Okay? This time we have a negative with the x. When you multiply x by a negative, that's when your graph reflects over the y-axis. And then a minus 5 from the function makes the graph translate down 5 units. Okay, over here we've got, again, a negative on the outside. That's a negative with the function. That makes it reflect over the x-axis. And then we've got the 4, which is actually going to vertically stretch the graph. Technically, we'd say vertically stretched by a factor of 4. And then a plus 2, not a plus 2 for the function, but a plus 2 with x. Add 2 to x, not the function. That's going to make the graph translate to the left 2 units. Okay? So again, very general, and we'll see how this would apply to other functions later, more specifically within the units, but this is very general. Okay? So let's work in reverse on these last two. If we took a function and we shifted it left 5, down 2, and vertically stretched it by a factor of 3, what's the equation for the transformed function? So I have f of x, that's my parent, has got to still be in there. Okay, if I wanted it to go left 5, then I would have to, excuse me, if I was going to go left 5, then I would have to add 5 to my x value. If I wanted it to go, here, let me change colors. Oops. Let me change colors so we can see clearly here. If I wanted to go left 5, then I would have to add 5 to x. If I wanted to go, what the heck? Sorry, I was trying to change colors and it didn't. If I wanted to go down 2, then I would have to subtract 2 from the function. So after the function, I subtract 2. And then if I wanted to vertically stretch by a factor of 3, then I would have to take my function and multiply it by 3. Okay, so there would be my new function. Alright, last one. Again, if you want to pause the video and give this a shot, knock yourself out, we're going to take f of x, take our function. We want it to go first. Let's see, it says make it go to the right 1. So if I'm going to go right 1, then I have to subtract 1 from x. And then if I want it to reflect over the x-axis, then I want to multiply my function by a negative. So the negative would be outside of the function. Okay? So this is very general, but again, we could apply this to specific functions. So let me just show you for an example here. Okay? If I took y equals x squared as my parent, and I wanted it to, let's say, go right 1 and down 4 and over the x and then compressed by a half or something like this, okay? Then my new function would still have the parent. It would still have the x and the square in it. Put that here for just a second, okay? So my parent would still be in there. Now if I wanted it to go right 1, then I would have to subtract 1 from the x. Okay, so subtracting 1 from the x, where I still have the x squared in there, but I have to subtract 1 from the x. Now if I wanted to go down 4, then after that function I would have to subtract 4. If I wanted to go over the x-axis, then I'd take my function and multiply by a negative. And then if I want it to be compressed by a half, then in between the negative and the parentheses there, I'd have to put in a factor of a half. Okay? And the purpose of this, again, is to be able to look at a function and know what's happening. So if I said, we're dealing with this function y equals x squared, well, you already have a concept of what that means. It means we're looking at a parabola. Well, if I said, here's our function now, we're dealing with the function that's got 3x plus 1 squared minus 2. Well, I know it's a parabola, and now I know that my parabola is going to be shifted to the left 1, it's going to be shifted down 2, and it's going to be narrower than the other parabola, or than the parent function, so that I could have a concept of this, right? Again, here's my parent. So just by looking at this function, I know that that the graph that I'm dealing with is going to be a graph that is left 1, down 2, and a little skinnier than my parent. So I have this visual of that function in my head. Okay? Now again, this isn't like essential that you can look at that function and know all those details, but it's very helpful to know. It makes you a little more fluent in the mathematics, particularly the farther you go. Okay? So again, these are very general concepts. We're going to talk more about them as we move along, but hopefully that's good for you to get going in this process. But as always, if you need any help, just reach out. I'm here for you. All right, guys, take care.